Good afternoon. Thanks for joining us. My name is Graham Cunningham. I'm a senior account executive with Brickeye. We're delighted to be with you today to speak with you a little bit about the use of in-situ temperature monitoring of concrete for the means of calculating maturity and strength in real time, how that could be used to optimize your schedules in your project, get an accurate insight into the performance of the concrete on your projects, and also optimizing for cementitious material and reducing embodied carbon. So over the course of the next hour or so, we're going to walk through this presentation here for you, introduce you to the concept, talk about the science behind it, introduce you to our flagship product, Lumicon, our concrete monitoring platform, how that supports these efforts and the use of the maturity method. And then towards the end of the presentation, we're going to take a few questions and answers from the audience. So with that, I'm delighted to introduce you to Amir Azari. Amir is one of the co-founders of Brickeye, and he's our resident guru of concrete and our chief commercial officer, and he'll be the one today sharing this presentation with you. So over to you, Amir.
Excellent. Thank you very much, Graham, and thank you everyone for joining this webinar today. We'll have a Q&A chat box that you can post your questions, and we'll be happy to go through your questions at the end of the presentation. And so with that, I'm going to jump into this presentation if you can all see my screen. So as Graham mentioned, today we'll be talking about the concept of the maturity and how it can help the construction industry today with respect to maintaining or advancing the schedule, and also how it can help with optimizing the design mix and the amount of cementitious material in the concrete. So a quick overview about our company. The company was founded in 2014, based out of Toronto, and we offer a wide range of different type of industrial IoT solutions for construction industry. Obviously, concrete sensor is one of our flagship products and expertise in-house, but we have other type of solutions for infrastructure projects, for high-rise civil projects, and also we have solutions for industrial asset monitoring. But again, the focus of conversation today would be around our concrete sensor product. This is our global footprint. We have ongoing projects in all parts of the world today, in North America, Europe, UK, Middle East, Australia, Singapore, New Zealand, South Africa, and South Americas. And we're also working with the top general contractors, precasters, ready-mix suppliers. You see all the big names here, such as Bechtel, PCL, Kiewit. Again, very much focused on the civil infrastructure projects, and also high-rise projects. We also have government entities who are using the products today. So concrete sensor. Why we use concrete sensor today? There are two main reasons, and there are two concepts behind the using of concrete sensor. The first and foremost is for mass concrete placements, and again for infrastructure civil projects. When you have a mass concrete, they usually come with thermal control plans, and within the thermal control plans, you want to make sure that the concrete does not overheat, or the temperature differentials is within the limit. So there are a few standards that are talking about these numbers. As an example, for conventional concrete, you don't expect it to go beyond 158, 160 degrees Fahrenheit, around 75, 80 degrees C. Temperature differentials, you always want to keep it between the core and the surface, or the edge or the corner of the concrete at any location inside the concrete. You don't want the differential to be more than 35 degrees Fahrenheit or 19 degrees C. And so for those reasons, you really want to make sure that you can use a reliable product to monitor concrete, specifically in early hours or early days. to understand how the temperature is going through how the temperature changes during the curation process. But on top of it, there is a new concept that has been around for many years, but it is becoming to a reality maybe in the past decade or so. And this is the concept of the maturity that I'm going to talk about a bit later, and how we can use this technology or this concept of temperature sensors to also be able to tell the in-situ strength of concrete in real time. So how the strength is being achieved in the concrete over time. So the typical process and the typical practice in the industry today is to prepare samples whenever a concrete is being poured. And you prepare samples such as cylinders in North America or cubes in Europe, and or also in the UK. I've seen that both are used. And you prepare those samples. You usually leave them at the site for 24 hours. After 24 hours, the testing lab or the testing partner would take the samples to the lab. They would maintain them in the cure box, typically at 23 degrees C, based on the standards, and then you break them on certain intervals. And based on the results of the break test, you make a decision on when to strip the formwork. And also after the 28th day, you can have a full understanding of the ultimate strength, and so you will report it to the EORs or the engineers, the structural engineers on the project. So where the samples come from, where the idea comes from. The idea goes back to, I don't know, 150 years, more than 150 years ago, or sometimes even goes back to many centuries. The idea is that when a concrete is delivered to the site, we want to prepare samples and we want to break them to tell if the concrete delivered to the site is a quality concrete or not. Does it meet the spec? Does it meet the expectations or not? So that's great. For that purpose, to prove the quality of the concrete, that's a fantastic process. It's a standard practice, and we have no problem with that. But the issue comes when you want to use these samples as a representative of your mass concrete, of your slab, of your mat foundation strength. The reason being is that these samples, either in the form of in the shape of a cylinder or in the shape of a cube, they are a small volume. And how this small volume of the concrete could be a good representation of your mass concrete. Plus that, although, I mean, we have the same design mix here, but because the amount of material is different, cement and water, the pace of curation is much different than the pace of curation in your slab, in your mass concrete. And that's why, specifically in early days or in the early hours, that you want to use them as open air to know when to strip the formwork, when to know when you have hit the 70%, they mostly lag behind the in-situ strength of the concrete. Even if it, I mean, assuming that, and this is the scenario when everything is done completely perfect, I mean, in the perfect world. But we know that there are also errors in the preparation of these samples. They are prone to human errors also during the transportation to the lab. You don't know how they are maintained. And sometimes you also have to grind the surface of the cylinder to make it flat to use it in the machine. So that would also add some cracking, micro cracks or a stress to the surface. So there are so many uncertainties about the fact that how we can correlate these guys, these samples to your mass concrete out there, and also their curation environment. You're keeping them in the lab at 23 degrees C, whereas your mass concrete can easily heat to 70, 75, 80 degrees C at the peak temperature. So that's why there are many debates out there that how accurate these samples could be to tell the in-situ strength of concrete in real time. So for those reasons, back in 1987, ASTM proposed a new standard or a new concept called ASTM C1074. And that's based on the concept of the maturity. And it all goes back to the exothermic processes and reactions that happen in the concrete. And we know that concrete initially is the mixture of cement, water, and aggregates, or some additives. But the foundation behind the formation of a concrete is the reaction between cement and water. And this reaction would lead to the hardening of the concrete. So, and that would basically contribute, that would mainly contribute to strength achievement in the concrete, these reactions between cement and water. So ASTM was trying to propose an idea that if we can correlate these reactions to the strength achievement in the concrete, then we might have hit the jackpot here. So the thing is that if I can understand these exothermic reactions that are generating heat, and if I can measure this temperature based on these reactions and understand how this temperature can be correlated to the strength, then it is great. Maybe we don't have to break the cylinders or cubes to tell the in-situ strength of the concrete. By using a temperature sensor, we can say what's going on. So ASTM proposed this technology, this idea back in 1987, and it took a while to change kind of the methodology that is very common in the industry. But now we see this to be becoming more conventional, more common in the industry. It is becoming more widely adopted in the industry to use maturity instead of cylinders or cubes as openers, or to tell the in-situ strength. And today there are more than 29 DOTs, Departments of Transportation, in the US who have accepted maturity, and they're using it for their civil projects, for their infrastructure projects, instead of using the cylinders. And I have one example here that it's, for example, for VDOT, Virginia DOT, and they are using it for opening, they're using maturity for opening road to traffic, for concrete road projects, for transit project. And I'm gonna just read from their road and bridge specification book, which says that the contractor shall not open pavement to traffic until the specimen beams conforming to F herein have attained a modulus of rupture strength of 600 pounds per square inch when tested by the third point loading method in accordance with ASTM C78. And now this part is important. The contractor may use the maturity test method in accordance with ASTM C1074 to confirm the development of satisfactory strength gain to open the pavement to traffic, provided the maturity test results are based upon the same concrete mix design as using the pavement as approved by the engineer. So it shows that we need to make sure that the same design mix is used, and then if we meet some certain metrics, then we are able to use it instead of the break test. And now this could be a good segue to talking about the maturity and what maturity talks about. So as I mentioned, maturity is a technique, I'm just reading this blurb from ASTM, for estimating concrete strength that is based on the assumption that samples of a given concrete mixture attain equal strength if they attain equal values of the maturity index. And I'm gonna talk about the maturity index. ASTM proposing two different type of equations to calculate maturity. One of them is the Nersol TTF or logarithmic equation, and the other one is Arrhenius equation. And in those equations, we try to basically, the variables are the current temperature and the time interval for measuring this temperature, because we know that the temperature is just changing over time. It gets to a peak and then it gets to an extremum and then it comes back. It shows the pace of the reactions at the beginning. So if we can capture these temperature changes as quick as possible, and then also we consider the time, we consider the temperature, then we can calculate maturity. And the idea is that if there are two samples, regardless of the dimension, regardless of the size, if there are two samples that at the same period of time, they hit the same maturity index, then we can tell that if they are, again, both of them are the same design mix and they hit the same maturity index regardless of the dimension, then they have achieved the same strength. That's kind of the idea behind the maturity. And how can we understand the correlation between maturity and strength? In order to understand it, we have to do a calibration for the design mix based on what ASTM is proposing. So ASTM is having a general concept, a general proposal around the calibration, but obviously it's not set in stone. It is something that can change based on the type of the design mix and based on the expectation that we have for our concrete to hit a certain strength. So obviously, I mean, I cannot apply the same procedure for a conventional concrete that hits 70% in 7 days to an UHPC, to an ultra high performance concrete that hit 12,000 PSI in less than 10 hours. So these two are different. So we have to think about a different procedure or setting for this calibration. But generally speaking, assuming that we are talking about the conventional concrete, the idea is that we prepare 17 cylinders. That number again could change. We can discuss it design mix by design mix, how we should look at it. But what ASTM is proposing is to prepare 17 cylinders. We have 2 cylinders to read the temperature, to measure the temperature. And then we have the other 15 cylinders to break them on certain intervals. And for conventional concrete, it would be day 1, day 3, day 7, day 14, and day 28. So why do we have 3 cylinders for each interval? The reason being is that we want to break 2 of them. And if the difference between these 2 is beyond 10%, then we have to break the third one as well. But if it is within the 10% of each other, then we don't have to break the third one. And again, it doesn't have to be cylinder. It could be cubes as well. I mean, I'm just bringing up an example here. Whatever sample or whatever, or this calibration should be done based on whatever sample that we are using in our common practice. If you're using cubes, we have to use cubes. If you're using cylinders, we have to use cylinders. Perfect. So I'm having temperature sensor in 2 of the cylinders, and I'm breaking the other ones on certain intervals. What does that mean? This means that if I'm reading a temperature, if I'm calculating the maturity, it could be, and now I can correlate it to the temperature of the cylinder or the cube that I'm breaking, because we have to maintain them exactly under the same environment. They are coming with the same volume of concrete or ready mix, and they are all being treated the same way, right? So I can tell that if the temperature of this cylinder is, I don't know, is like 25, 30, 55 degrees C, then the cylinder that I'm breaking on day 7 is also having the same temperature. So it's an apple-to-apple comparison now. So perfect. Now, again, this is an example for the Nersal equation, but I can also use Arrhenius equation. So the Nersal, or the TTF, temperature time factor, says that I'm continuously measuring the temperature, and the maturity would be the summation of current temperature minus the datum temperature, and the datum temperature is the temperature below which the concrete does not cure. It can change design mix by design mix, but a very conservative number is 0 degrees C. So, I mean, many researchers and reports are saying that we can safely use a 0 degrees C as the datum temperature. So again, summation of current temperature that we are measuring minus the datum temperature times delta T, which is the time interval. And ASTM is proposing every half an hour, but the higher rate of sampling and measurements, the better. So we propose that we do it at least every 15 minutes. So now with this, I have maturity versus time. So I'm calculating maturity continuously using the temperature sensors inside the cylinders or cubes. So I have my maturity versus time. Then we are also breaking the cylinders or cubes, and I have the strength versus time. M1, S1, M2, S2, and so on and so forth. Now, with having this set of data points, I can find the best equation or function to correlate strength to maturity. And this maturity curve or this calibration profile or this basically equation would be the signature of your design mix, which is regardless of time and regardless, which is basically independent of time and independent of volume. So I know that whenever my design mix hit this maturity number, I know that this is the strength. So if you tell me that I have two different samples, one of them is, let's say that, for example, I have a slab and I have a small cube. So both of them in 24 hours, okay, now I want to calculate maturity in both of them after 24 hours. So in the slab, after 24 hours, I might hit 300 TTF. And in the cube, I might hit only 200. So it means that after 24 hours, this one has achieved a higher strength compared to the cube that has only hit 200. That would give me a lower strength. So that's kind of the idea, to understand the correlation between the maturity and the strength achievement in the concrete. As I mentioned, there are different design mixes. We have conventional concrete, we have ultra high performance concrete, early strength concrete, and so on and so forth. And each one of them would obviously have a different behavior and with different pace or rate of curation and strength achievement. And for that reason, we have to do this calibration for each design mix. I mean, I cannot get a calibration profile for one design mix and apply it to the other design mix as well. And we also need to be understanding that it's not just one type of equation or function that could apply to all different type of design mixes. Again, ASTM is proposing Nersel and Plowman equation. Plowman is a logarithmic equation. But we have seen that for early strength concrete, you need to consider different type of equations because Plowman doesn't give you the best fit for a high early strength concrete. Something that, for example, hits 70% or 80% of a strength in a couple of hours. So for that reason, we have been also been very understanding of this, and we know that we need to have something like a modeling software to understand which equation do we have to use Plowman or no, it have to use Peterson, hyperbolic parabolic equation, and so on and so forth to understand the best equation and calibration profile for our design mix. So a very, very fair question here is that how do we compare? How can we tell that maturity is accurate compared to the samples? Okay, perfect. These are all textbook examples, and these are all coming from a standard. But do we have some data to show us the accuracy of this in practice? Yes. So we have done some experimental with our partners, and this is one case study where our clients prepared the mock-up trial, prepared the setup for the mock-up trial. They set up the formwork and the rebars, and then they used our technology. We did the calibration on the design mix. We used our technology to calculate maturity and strength. They did the break test, and we decided to use the core test as the benchmark. We are all familiar with coring. Coring is fairly accurate, but it is obviously expensive and destructive. So it's not very favorable in the industry for obvious reasons. So as you can see, on day 5, the break test was showing 56 MPa on that specific design mix, whereas the core test was showing 76 MPa, 20 MPa difference, more than 50% difference in the data. And our Lumicon system, based on the maturity method, was exactly on par with the core test showing 76 MPa. On day 7, it was 71, core test was 80, and again, we were on par with the core test. So now we could also ask another question. why on day 5 we have 20 MPa difference, and what happens that in day 7 we only have now 9 or 10 MPa difference. As I mentioned, it's all about the early days. It's all about the pace of curation at the early days, early hours. At the end of the day, we are expecting the ready mix to hit the ultimate strength after 28 days. So eventually they would overlap. But what is important to us is the earliest strength that we could use as opener. We know that when we hit, I don't know, 70, 75, 80% of this ultimate strength, we can strip the formwork. So we want to understand how we can strip the formwork faster to advance our schedule without wasting time. So there is tons of value in understanding that how quick we can hit that 70, 80% of a strength to make some informed decisions. At least even if you don't want to advance your schedule, we can maintain our schedule. And for that scenario, for our client, these strength values could be equivalent to 3 days of saving per pour. And let's think about it. What is the average number of pours for a high-rise building, for example? Maybe we have 100 pours, 50 to 100 pours. Let's take 100 pours. I mean, we are doing 2 or 3 pours per floor. We have mat foundation, we have columns, and so on and so forth. So 100 pours. I'm not saying 3 days. Even on average, we are able to save 2 days per pour. That's equivalent to 200 days of saving. Equivalent to 6 months of saving. Let's think about it for a moment. That how much value it can add to the project if we can push the schedule by 6 months. And we are not doing a magic here. We are just talking about the reality. We are talking about the fact that our concrete has hit the number that it has to. So we are just wasting maybe 4 to 6 months on our project because we don't have a knowledge about the in-situ strength of our concrete after being poured. So the value is not about in-situ strength, but compared to the samples or cylinders, the other value here is that we may also be able to use this technology to optimize our design mix. I mean, we had another client that they were kind of on the 3-day schedule for form stripping, and they were thinking that it's an early strength concrete, and probably it's not possible to have the 80% of the strength even earlier than 3 days. So we worked with them, and as you can see, we had to use a parabolic hyperbolic equation, and we proved to them that their concrete hit 80% of its strength in less than 10 hours. So they're technically wasting 48 hours because they were waiting until day 3 to strip the formwork. And they came to us and they said that, hey, we are not a self-perform project. We are not a self-perform company. And I cannot ask the crew to come to the site earlier. I said, all right, that's not a problem. But at least this gives you some visibility with respect to opening a conversation with your engineers and ready-mix suppliers to optimize your design mix. Maybe it is over-designed. Maybe you're using lots of cementitious material. And now we can optimize it. We can probably reduce the amount of cementitious material. You have to wait for 3 days. So why you want your concrete to hit 80% in 10 hours? You can technically wait for 3 days. You can now optimize the amount of cementitious material that would also reduce the amount of embodied carbon and the overall carbon footprint that you have through your project. You can optimize it by reducing the amount of cementitious in the cement, in the concrete. So, and the other value here is that you may say that, you know what, I haven't seen that much difference between my samples and the slabs. So is there any other value here that I can get? So we talked about how on average you can save a schedule by 2 days per pour. We can talk about the fact that you can also optimize your schedule, but there are obviously a third value here as well. Even if you tell me that there is no difference between the strength in my samples and in my slabs, what is the third value? The third value is having continuous, remote, and real-time access to data. And I have an example here. The example here is that, again, this is a this is another trial that we did with another client back in 2018. So this is the strength that we calculated based on the maturity method. As you can see, I mean, it took it about, so it was a 30 MPa concrete, and we were showing that probably, I mean, you can hit that 21 MPa in about 3 days. But guess what? They were breaking the cylinders on day 1, day 2, and day 5, because they were thinking of stripping the formwork on day 5 or day 6 or day 7. But because they didn't have real-time access to the data between day 2 and day 5, they had to wait until day 5 to hear back from the lab. And so the actual time of formwork removal is day 5. Whereas using this technology, by having real-time and continuous access to the data, you have the option of stripping the formwork on day 3, which is equivalent to 2 days of saving. And that's the other value we can get from this technology. So advancing the schedule, optimizing the design mix, cementitious material, and having real-time, continuous, and remote access to the data about the in-situ strength in your concrete. So now maybe I'll also quickly talk about the technologies that we can use here. So Lumicon is a very, very advanced technology for concrete monitoring. First of all, I mean, if you want to use it for maturity, you want to make sure that you are not using thermocouples for maturity. You want to make sure that you are not using low accuracy products, because maturity is very dependent of continuous measurement of temperature and continuous calculation of maturity. So think about it. Every 15 minutes, you're measuring the temperature. And if you're using a product that has a low accuracy, then you will end up with a high accumulated error at the end of all your calculations, which is not ideal. So that's why, I mean, in our technology, we are using a kind of automotive grade, very advanced digital sensors with an accuracy of plus minus 0.2 degrees C. And for comparison, the accuracy of thermocouples are between 2.5 to 3 degrees C. So that's why thermocouples are not ideal for this. Second of all, you may need to do calculation of basically you want to look at the strength, you want to look at the maturity at different locations inside the concrete, because obviously at the core you might have a higher pace of curation versus the surface, which is more exposed to heat dissipation and because of the air convection and so on and so forth. So for those reasons, we also have a distributed sensing solution, which means that we can have all these advanced high accurate sensors, 30 of them along a single line of cable, and very armored ruggedized cables that, again, that they could be embedded in the concrete, and then you can do the entire profiling around your concrete at different locations to see the temperature values, to calculate maturity and strength. And then we have made it very easy to use, plug and play. You only need to connect the cables when they are installed next to the rebar to a transmitter node, to a small box that I can show it to you here as well. It's a small box that is a wireless transmitter and a data logger. Once you plug the cable to the node, it would wake up automatically, and it starts sending data to the cloud right away. So you don't have to go to the job site to collect the data, and you don't have to set up a gateway. You don't have to provide power. You don't have to provide internet, Wi-Fi, or anything. Everything is basically, our clients are fully hands-off. So when the cable is plugged to the node, then they can go back home and check the data on their phone. Maturity, strength, everything. Easy to use, easy to access the data, and continuous and remote access to data. And also we have a solution for remote projects where you don't have access to cellular network, because our Luminode Plus product used the cell network to send the data to the cloud. For a remote site, we could have also another setup to use a gateway sitting close to the trailer where you might have Wi-Fi or wired internet. And I have an example to show it to you. So even for remote projects that there is no cell coverage, we can still provide, again, the mandate is to provide continuous and remote access to data. So these are some specs. This is the Lumicon Plus product, which is FCC certified, and it's a required certification for any wireless device that you use. And it comes with a rechargeable battery, and the expected battery life is between 4 to 6 months. And but obviously you can charge it overnight. So you only need to charge them 2 or 3 times a year, and then you can use them for 5 to 10 years. So these cables, very armored, very ruggedized, very high quality product. And as I mentioned, the accuracy can be within plus minus 0.3 degrees Fahrenheit or 0.2 degrees C. And I can have up to 30 sensors. These black shells that you see on the cable, they all have digital sensor in them, and I can have 30 of them along a single line of cable. We also have some special cables for smaller ports, and they are also armored, but they're single points. They're like a probe if you want to do single point sensing. Some installation pictures, the cables that are installed next to the rebar, and then you just plug them to the node. Once the monitoring is done, you just unplug the cable from the node, and then cut the cable flush to the surface of the concrete. These gray areas, these are all the armors that we have inside the cable. That shows how strong the cables are. So with this product, you don't need any redundancy, technically. Very sophisticated software, both mobile application and online dashboard. Very sophisticated, and at the same time, very, very easy to use. I mean, it provides all the data that you need, graphs, customized reports. You can have customized reports, whatever format of the data that you need, format of the graphs. You can customize it. You can customize it on the software, so we can receive them automatically on certain schedules, like every 4 hours, every 6 hours, every 10 hours. You also have access to the raw data. Our clients take the ownership of the data. And again, you can access the data both on the phone and on the dashboard. In summary, it's a truly remote monitoring solution. Again, you don't have to be present at the job site to collect the data. It provides very, very reliable connectivity. I mean, we have clients in the UK who are using it in different cities right now and are super, super happy with everything. Very advanced product. And it's a very rugged and dependable product. It's not, again, like flimsy sensors like thermocouples or a cumbersome set, or it doesn't require any complicated setup. Just plug and play. You get the node, you get the cable, you plug it, you go back home. That's it. And then they do the pour, and then you can access the data. Rechargeable, reusable, and as I mentioned, the cables could be tailor-made based on the pour requirements. So in summary, this technology helps with quality assurance, specifically for mass concrete placements. It can help with the schedule optimization, design mix optimization. And the last thing that I want to mention about this ecosystem is that curation of concrete is not just about inside the concrete. You're pouring concrete in outdoor environment that is exposed to heat, to sun, rain, cloudy. So many things could happen, right? So you also want to be able to monitor the ambient conditions, and we have understanding of these requirements. So we have a kind of an ecosystem, combine it with our micro weather station that helps with monitoring, again, remotely and real time the local weather conditions, like such as temperature, humidity, precipitation, and so on and so forth. Sometimes, I mean, this happens in Canada a lot. I'm sure that it happens in the UK as well, that you have to use the space heaters to ensure that your concrete is going through that curation process as expected. So we also have a system to monitor the heaters, to instrument the heaters, to work closely with our concrete sensors in a way that we collect the data from the concrete sensor, and then we can instrument the heaters to have them automatically and properly turn on or turn off or adjust the temperature output from the heaters. And also we can have a matchbox that we can talk about. I mean, if you have any questions about it a bit later, but that's a box that would synchronize the temperature inside the cure box with the temperature of your concrete, so your samples are exposed to the similar temperature in real time. A few case studies. So this is a mass concrete placement. It's a Patula Bridge in British Columbia. You see that this rugged cable is used for a cage, for piling, and how we can use this technology to do temperature profiling of the entire cage, again, to avoid bulging, cracking, and so on and so forth. Some examples for the high-rise projects, testimonials from our clients that how they have been able to save thousands of dollars, like this one, saving $20,000 to $50,000 daily in overtime and weekend work cost, 50% reduction in concrete testing cost, because using this technology can also minimize the number of samples that you have to break, right? You only may need to have breaks for 28 days, right? I mean, just to prove to the engineer that you have hit your strength and is a quality concrete. And again, this project, average schedule saving of 2 days per pour. We also had some cases that using our technology, our clients realized that during the weekend, the concrete temperature has dropped significantly. There was no one at the job site. They sent someone to the site and they realized that one of the heaters had run out of fuel. So they could save concrete and prevent and avoid the rework. This is a concrete dam project by Kiewit in Northern Ontario. And again, that site is a site that was remote area with no cell coverage, but we were able to set up a system to boost the signals from the nodes about 2 kilometers away to a trailer where they had access to wired internet. And so again, we were able to provide remote and real-time access to the data, even for a remote site with no cell coverage. Again, an airport project, a mass concrete placement under the taxiway that they also used our technology for monitoring the quality of concrete. So that's pretty much it. I'm hoping that this conversation kind of sparked some questions. And again, I want to thank you for the time, but happy to answer any questions if you may have.